All right, let's consider the motion of gases, and we're going to look at effusion and diffusion. Now, these are not the same thing, so let's take a look. Now, effusion versus diffusion. Diffusion is simply the motion of the gas through a space. Containers, it might be the case. Now, this is going to be a random process where all the gases are moving in their own special or specific directions. Now, effusion instead of diffusion is where a gas is going to be moving through a small hole. When this happens, it starts to force the gas to move along a path, and it does it one at a time. So you start to look at the speed of how their molecules are actually moving in an organized direction versus the fact that sooner or later they're simply going to get mixed up. So if I considered moving uranium hexafluoride through a system kind of like this. So what happens? As uranium hexafluoride moves through, uranium hexafluoride has got a couple of different isotopes. So we have uranium-235, which is the one we want, versus uranium-238, which is going to be the heavier one, which is not what we really want for, in this case, either a nuclear power plant or something on that nature. Because the uranium-235 is lighter, it is going to shift through or effuse through this barrier. It is also going to actually move faster, and we can use this to separate out as a function of A, how fast or how small they are, allows us to separate them. So we have an equation for this. If we're doing a fusion, we're going to do the rate of some molecule A over a different one, obviously through the same container or the same space, is inversely proportional to the molar mass. So why is this the case? Well, first of all, the kinetic energy of a gas is going to depend on the mass multiplied by the speed squared. Now, the kinetic energy of our gases is the same if the temperature is the same. So kinetic energy, we also know, depends on T. So kinetic energy is going to depend on temperature here. And for all gases at the same temperature, they have the same kinetic energy. But kinetic energy depends on the mass times the speed squared. What does this mean? This means that as the mass goes up for a gas, the speed is going to go down. The lighter molecules are going to move faster. So if we want to compare the rate of hydrogen over the rate of neon, it's going to equal the square root of the molar mass of neon, which is 20.18 grams per mole, over the molar mass of hydrogen, 2.02 grams per mole. And when I do the math on this, I'm going to get 3.16, which tells us that hydrogen moves or effuses 3.16 times faster than neon. Why? Because it is much lighter. So as gases get hotter, if we look at the distribution of their speeds, it goes from being a fairly sharp curve where this is the speed versus how much of the molecule we have. As it gets hotter, this kind of levels out. But if we have molecules that are at the same temperature, then the speed is going to depend on the mass. So if we look here at helium and we look at its average mass, helium on average is moving much, much, much faster than neon, which on average is moving much, much, much faster than xenon. The heavier it is, the more slowly it is going to move. So that's speed and kinetic energy, but our issue is, can we always use the ideal gas laws or the ideal gas law? Well, here's the problem. If we take and we put gas into a container and we start out with low pressure and then we take and we consider really high pressure. As we get to higher and higher pressure, the volume of the container that is occupied by the gas molecules goes up. and the gases become significantly less compressible. They just don't have as much space. And the volume of the gas is actually going to start to depend on the number of gas molecules. So we assumed that gas molecules themselves had no volume and that the volume of the gas was the volume of the container. Well, the problem is at high pressure, that is not the case. These gas molecules start to occupy space, but that's not all. The other problem that occurs is that molecules interact. And one of the main things they do is they start to attract. So as molecules in a gas start to attract each other, its apparent volume is going to change. And these molecules, particularly as they get cold, so as the molecules get cold, not only do they start to attract, if you had water as a gas and you tried to work at STP, well, STP is 0 degrees Celsius, and that in fact would be ice, which means it's no longer a gas. As molecules start to get very, very cold, they do not behave at all like an ideal gas. And we have problems with attracting with the containers. We have a problem with attract with another gas, and then we have a problem with just how much pressure they're going to exert. So there's a takeaway here. And the takeaway is that we want our real gas to behave ideally. Well, if that is the case, we want to make sure that the volume of the gas molecules is small, and we want to make sure that gas molecules collide elastically, that they ignore each other, that they don't stick to each other. Well, the best way to do this is to have, if the volume of the gas molecules is small, this means that there are going to be very few molecules, which means that we're going to work at low pressure. And if we want these guys to collide elastically, we basically don't want them to stick together, which means that we have to work at high temperature. So the takeaway on gases, if it all else fails and you want to do this and you want to make this gas behave ideally, work at low pressure and high temperature.